Welcome back. This is part 2 of this derivation for this equation, which is delta F, which is the additional force required by F1 or 2F1 to be able to move piston 2 up by a distance of d2. Now, just a quick note, all of my notes for this derivation are in the description below, so you can just get a PDF of the actual derivation if you don't want to really watch this video or just use that as a supplement. But we are going to continue on from where we left off in the last video, and that was really studying this state A and state B, and we had these two equations, the equation for F2 here, and the equation relating the two volumes of liquid that we displaced when we pushed down piston 1 by a distance of d1. So I know this diagram on the right is getting a little bit messy, so what I'm going to do is I'm going to take this diagram, still state B, and I'm just going to redraw some things and we'll go from there. Okay, so all I did here was I just redrew state B in a little bit of a cleaner fashion. So remember, for piston 2, let's quickly look at this diagram. So piston 2 has now moved up by a distance d2, and so force 2, which is, the force caused by whatever object that is on top of piston 2, is now at this line. And on the left here, we have this additional force delta F that's added to F1 to move piston 1 down by a distance of d1. So piston 1 is now at this line, and piston 2 is now at this line. So remember, we are trying to derive this equation right here. What is delta F? How can we determine what delta F here is based off of this new system plus these two equations that we looked at in the previous video? Well, remember I said that this entire system, this hydraulic system, is in hydrostatic equilibrium. Mass density is concept. So we can use what we know about pressures to figure out what delta F is. So the very first thing I want to do is I actually want to determine what the pressure of the liquid is right here where piston 1 is located. And remember, for liquids that are in hydrostatic equilibrium, pressures along a vertical line through that system all have the same pressure. So in other words, the pressure at this line, or all points along this line right here, are going to have the same pressure. So I'll just say equal pressure. Let's actually determine what the pressure is for piston 1, or in the 1 region, right here. So I want to figure out what the pressure is right there. And what I'll do is I'll just call that pressure 1, and then pressure 2, which is on the piston 2 side, I'll just call that pressure 2. And we know that pressure 1 and pressure 2 are going to be equal, right? Pressure 1 is equal to pressure 2. Okay, so what is pressure 1? So pressure 1 is going to be, well, first, it's the pressure caused by the force and the additional force, so F1 and delta F. So I'll just say F1 plus delta F, right? The additional force added to F1 to move piston 1 down, divided by area. Area is A1, so we really just have force over area, right? That's pressure. Now we have to add on to that any initial pressure, P naught, which is at the top of the piston. So P naught is located right here, and that could be open to the atmosphere. In this case, it is. Plus, we still have to add the pressure caused by the liquid, so plus rho g d, and d is just regular d, not d1 or d2. And remember, d is the distance from P naught down to the point that we're studying, and that's going to be a positive distance. But if piston 1 is already at this line, that is where P naught is, right? This line right here is open to the atmosphere above, and we're studying P1 right at that line. So in this case, D is actually going to be 0. So this term right here is going to go to 0. Now let's look at pressure 2, which is, again, along that same line here. So I'm going to say pressure 2 is equal to, well, again, same thing. So the first pressure caused by piston 2 is F2 over A2, right? Force over area is pressure, and that is just the pressure caused by F2. And we're going to add to that P naught, which is, in this case, just atmospheric pressure, because piston 2, which is located right here, is open to the atmosphere. And then we're going to add to that rho GD. So rho GD. Now, what is D? So I'm just going to have a blank space here, right? This is what D is. But what exactly is D? Remember, D is the distance from P naught down to the point that we're studying. So again, piston 2 is now located here, right, in state B. So this is where P naught is. So the distance D is going to be from P naught all the way down to the point that we're studying, which is down here, pressure 2. And that distance, so the distance from here to here, is actually D2 plus H plus D1, right? We have to add those three distances to get from where we are here down to this yellow line where P2 is located. That D is D2 plus H plus D1. Now we have these two equations for pressure 1 and pressure 2. Now remember, pressure 1 and pressure 2 are equal, so we can actually set these two equations equal to one another. So pressure 1, remember, is F1 plus the additional force over A1 plus P naught is equal to F2 over A2 plus P naught plus rho G D2 plus H plus D1. Okay, so I just set those two equations equal to one another. Now, the very first thing you can probably see is that these two P naught values cancel out, right? They're constant, they're both the same in both equations. So those two terms cancel out. And what we're left with is this equation. So F1 plus delta F over A1 is equal to this term here on the right-hand side. And now what I can do is I can multiply both sides of this equation by this A1 term. So on the left, we'll just get F1 plus delta F. And this is what we left with when we multiply A1 by both sides, right? We have this equation right here. Now, what I want to do is I want to go back to this equation. So remember, state A was just the hydraulic system in equilibrium before we applied this additional delta F, which you can see in this diagram, right? So state A is before we applied that additional force. So we're going to take this equation and we're going to plug it in for this F2 term. So I'll go ahead and copy this equation down below. So I just took that equation and I just copied it down here, right? So what we're going to do is we're going to plug in F2 into this equation. So this is what F2 is equal to. So I'll move this down a little bit and we can go ahead and do that here. Okay, great. So this is what we are left with when we take this and we plug that into F2. So this right here is that F2 value right here. And I just rewrote this A1 over A2 right here, and then we have this term right there. Now I am going to simplify this even more, and so the first thing I'm going to do is multiply this A1 over A2 term into this part of the equation. So we can go ahead and do that now, and that is going to leave us with F1 plus delta F is equal to, well, we have F1 times A2 over A1, right? And we multiply that by A1 over A2. We're just distributing this term into both of these terms, right? Simple multiplication. Minus rho GH times A2, and that is going to be multiplied by A1 over A2. Now, what I'm going to do for this second term is I'm actually going to simplify this. So I'm going to multiply A1 into each one of these three terms, as well as rho and G into each one of these three terms. So what I'm left with are three different subterms, I guess. So rho G D2 times A1 plus rho GH times A1 plus rho G D1 times A1. This term, I just converted it into this term right here. And this term I converted into kind of this section right there. Okay, so there's a lot of things we can do here. The first thing you'll notice is that this A2 and this A2 cancel out, and then the A1 and the A1 cancel out, as well as this A2 and this A2 cancel out. So what we're left with is F1 plus delta F, the additional force, is equal to F1 minus rho GH times A1, right? That is this term right here. And then we're going to add to that rho GD2 times A1 plus rho GH A1 plus rho GD1 times A1. Now you can see here that this term, rho GH A1, cancels out with this term, rho GH A1, right? We have a positive rho GH A1 and we have a negative rho GH1. So, or HA1 and that cancel out, as well as this F1 and F1 terms. They are present on both sides of the equation, so they are going to cancel out. And what we're left with is delta F is equal to rho GD2 times A1 plus rho GD1 times A1. Okay, we are almost there. So this equation is starting to look a lot like this equation, right? What we're trying to derive. So we're almost there, but we're not quite there. Now, I want to bring your attention back to this relationship here from state B, where we equated the two volumes, so this volume and this volume, and we said A1 D1 equals A2 D2. So I will bring that equation down below, and we can use that to simplify what we have to hopefully get this equation right here. And if we don't, then this was a complete waste of time, or I messed up somewhere in the calculation, but I feel pretty confident. So let's go ahead and take this, and I'll see you down below. Okay, so I just took that equation. It's sitting here on the right side. And what we're going to do is actually look at this big term right here. And you can see that we have some common factors, rho, G, as well as A1. We want to figure out what delta F is, the additional force to raise piston 2 by D2. So we want to keep this D2 term here. So what I'm going to do is, you can see here we have a D1, A1 term, right? And that D1, A1 is this same term here on this equation that we brought over. So I'm going to substitute A1, D1 for this term right here. And what that leaves us with is delta F is rho GD2 times A1, nothing changes there, plus rho G D1, A1 is really D2, A2, right? That is just this term right here. And again, we can take out rho, G, and D2 in both of these terms and simplify it a little bit. And that will leave us finally with rho G A1 plus A2 times D2, right? This equation here is just a simplified version of this right here. So there we go. We finally did it. It took us 2 videos, but we finally figured out what the additional force we need to apply to F1 is in order to raise piston 2 by an amount of D2. Now we're going to use this equation in some future problems and examples, but now that you understand the derivation and the theory, you guys are going to be masters in fluid mechanics, or at least for the hydrostatic or hydraulic lift systems. So I hope that was pretty fun. I do definitely enjoy these videos. Again, the notes for this derivation are down below in the description. So I hope that helps. And with that, I will see you guys in the next video.